afternoon. I'm going to kind of move into the more modern here, talking about some Jurassic springs as well as some modern springs. But first I want to talk about biosignatures. So my research, I focus less on ancient terrestrial biosignatures, and I look more towards extraterrestrial biosignatures and potentially what we'd be looking for on Mars. So one of the things, what a biosignature is, we're looking for some fingerprint of life, chemical, morphological, or mineralogical. Morphological, I'm going to focus on morphological in this talk, although that is kind of the thinnest evidence. And these are preserved in sedimentary rocks. And we kind of have to look at, when we're looking at biosignatures, and particularly when we're looking at a strategy for extraterrestrial searches for these, such as on Mars, you need to look at the specific environment. So you need an environment that has high production potential, and you need an environment that then also has high preservation potential. So what I do is I look at the taphonomy, or how these things are being preserved over geologic time. So because water-rock interaction, and as we've seen with the previous two talks, really bad things can happen to your signs of life in your rock, given enough time. And when we're sending rovers to Mars, we have limited resources, we have limited time, we have limited energy, we have limited measurements, so we need to identify targets that are, we need to be able to identify macroscopic features that will help us identify potential biosignature targets. So springs, both hot and cold springs, have excellent preservation potential. They also have excellent production potential, but nevertheless, biosignatures are ambiguous, okay, as we've seen. So most research on biosignatures is done on either very ancient rocks or modern environments, and this diagenetic alteration, the water-rock interaction that happens over geologic time, can be significant, and we don't really understand what is going on and what exactly we should be looking for, okay? Another point I'd like to make is that ancient terrestrial environments are potentially and probably much more altered than similar aged environments on Mars. So I look at Jurassic age rocks, and that is probably a better, an analog in terms of diagenetic alteration, because it's going to be limited on Mars. You don't have the burial, you don't have the depth of burial. And you don't have the heat that we've seen, this metamorphic stuff going on. You don't have the water-rock interaction for billions of years like you do on Earth. Okay. So my talk is split up into basically two parts. I'm going to talk about how to recognize spring deposits in the rock record, which is very important. And we're going to look at some sites on Mars for comparison. And then I'm going to talk about microscopic biosignatures and how these are altered over geologic time. Okay. So my study area here, we have, whoops. There we go. So my study area here is in the western United States at a place called 10 Mile Graben. The Morrison Formation is a Jurassic siliciclastic kind of fluvio-lacustrine unit overall. And there's this Lake Tudici, which is an alkaline saline lake in the upper part of the Brushy Basin. that I'm not working on. My study area is a little bit off of that interpreted lake, and this is actually an interesting site because it's this big, thick carbonate. The Brushy Basin doesn't have carbonates in it except for here in any big amount, but this is about 10 meters thick carbonate. It's spring-fed, likely hot spring-fed lacustrine carbonate, similar to Mono Lake in California in the U.S. This is topped with a microbialite that's about 3 meters thick, and underneath is a mud rock with silica-rich lenses interbedded in that mud rock. Also in 10 Mile Graben is a series of modern cold springs and geysers. Now this is unrelated to the Jurassic deposit, it's just in the same area. But this is a series of CO2 and hydrocarbon charged circumneutral springs with actively precipitating microbial mats. There's a lot of carbonate and iron oxyhydroxides. But the interesting thing about this site is that this spring has been emanating for about 400,000 years. So you end up, so there are a series of progressively older tufa terraces preserved on paleo land surfaces in the area up to 400,000 years old. So the purpose of this is to characterize these spring deposits and the biosignatures, and then look at how they're changing over geologic time, and then produce diagnostic criteria to recognize these units in the rock record and on Mars. So I am giving the punchline first, and I had already thought of this before today, of giving the conclusions first, so here's some of the Mars sites. Here's a comparison. Here's a modern spring, and then these progressively older terraces, and then the Jurassic rocks. And we see a lot of these same features, and a lot of these same features in particularly like Gusev, which has been proposed as a hot spring deposit. Marias Pass at the Murray-Stimson contact has some very similar features, and I suspect that's a spring deposit. The Gillespie Lake member, this is probably more microbial mat, or it's been proposed, I'm sorry. Please don't think that I'm proposing that there is microbial mats on Mars. It has been suggested that these are morphologically similar by Nofke et al. Last year, and so potentially they're very morphologically similar, which is, as I've said, a very thin proof. We need much more evidence before we can say those are microbial mats. So before you come at me with chains and knives. Some of these macroscopic features that we observe are present in these modern mats. There's some wavy laminae. They're present in the 100,000-year-old mats, and also in the Jurassic. And then this is from that Nofke paper, and here's some wavy laminae that she has noticed, and that she has noticed has similarities to this. Now, on Earth, we typically look at that and say, that's microbial. So, it most likely is on Earth. It may or may not be on Mars. Okay, here's another feature. These are terracets, or as we've been calling them, kind of delicate features. But these terracets have also been proposed as a biosignature. They are being preserved on geologic timescales. There's also some similar features which you cannot see in this picture here. You can see it on my computer. Similar features on Mars. One thing is that we are seeing some degradation and recrystallization. There is a lot of Ostwald ripening going on. as this carbonate is recrystallized and becomes a little more massive over geologic time, but nevertheless, they are still being preserved, okay? So, as I said, there are these silica-rich lenses within the mud rock, and these are bedded. And within the bedding, there's actually some wavy lamination, and we see similar features at Marias Pass in Gale Crater. Okay, so here's just some other pictures. This is a silcrete or a silica-rich lens directly under the carbonate. Here are some silica infilling of fractures, and then this is what that looks like in outcrop. Here's the massive carbonate, here's the mud rock down here, and then these silica-rich lenses are present within the mud rock. Okay, so at Marias Pass, at the Murray-Stimson contact, we see these similar kind of silica-rich lenses that have some lamination. They have high-temperature minerals in them. The overlying rock has some silica-rich fracture kind of fill, or the selvages have this silica-rich signature as well. And I suspect that due to these similarities that is probably a spring deposit. Here's an alternate way you can get a silica-rich lens, or a silica-rich fracture fill, I mean. So this is also in 10 Mile Graben, where this spring system is. So this would be related to the modern spring system. This would have been a fracture within the rock underneath a paleo land surface, where fluids moving up through this fracture and then emanating out onto the paleo land surface that has now eroded away in the last 400,000 years. And with aerial data, this would look enriched in silica because the cement has been removed. So relatively, it's enriched in silica compared to the red host rock over here. See ya. There's a picture to compare. Okay. So another feature that is very common both on Mars and on Earth, and this is really, it just is forming from subsurface fluid flow. It doesn't necessarily need to be a spring deposit, but certainly diagenetic fluid flow. It's independent of temperature, and it can be kind of any mineralogy. And, you know, but this is, like I said, it's diagenetic. It doesn't need to be, it doesn't need to be it doesn't need to be a spring, but it can be a hydrothermal system that's, you know, flowing through your rock and out up onto the surface. But these are important because they're recording your subsurface fluid chemistry. So whatever's going on in the subsurface, which is also it's actually a potentially habitable, modern habitable environment on Mars. It would be probably the only habitable environment on Mars today, if there is one. And certainly, if there was a habitable environment in the subsurface, it would represent the longest lived one. So it's important to study these things because you get a handle on what's going on down there in terms of chemistry and habitability. And these are all over, you know, so you've got gypsum veins all over Gale, Gusev, and Endeavour. Okay, so we'll move on to microbial biosignatures. So here's some from the modern springs. This is kind of a early lithified microbial features, and you can see there's this kind of diffuse iron oxyhydroxide that's encrusting them. This is 100,000 years 100,000 years goes by, and you have some recrystallization of the iron oxyhydroxides. So there's some degradation, but there's still, the segmentation is still recognizable. And what we're seeing is this Ostwald ripening as these smaller crystals are being lost at the expense of larger crystals. And there's probably, these are probably more amorphous iron oxyhydroxides that are just dehydrating to more stable phases. Okay. I think part of the most interesting stuff, so in the modern mats, you see these tubes that are very ubiquitous. And you see these kind of as you get older, you continue to see them. You also see these tubes associated with these kind of honeycomb structures. Here's a 400,000-year-old honeycomb structure. The interesting thing is that in the Jurassic, these tubes are still present and surrounded by these honeycomb structures, but they're being entombed by this massive carbonate. So you're having this Ostwald ripening that is kind of degrading some of the macroscopic features, but it's actually entombing your microbial body fossils and preserving them, which actually bodes well for any spring deposits that might be present on Mars. That would be, you could protect these from UV damage and all of those other nasty things that go on because you've entombed them. So there are also these hollow spheres. This is a 400,000-year-old, and they're associated with this honeycomb structure. So it looks to me like there's these spheres are a potential source of the honeycomb structure, which means these honeycomb structures are actually microbial trace fossils, which a trace fossil is like a worm burrow or something like that. It records the activities of an organism. And so that's interesting. I mean, you don't have to have the body fossil preserved. You can have a trace fossil preserved, okay? So in summary, we're preserving some macroscopic features on geologic timescales, these delicate textures, terracets, these silica-rich bedded deposits in the mud rock, and veins are all preserved on geologic timescales, and they're recognizable, and they point to a spring deposit that is preserved in the rock record. And these features are preserving microscopic microbial fossils as well as microbial trace fossils. And then just to reiterate, we're seeing, the big take-home message here is that these spring deposits have a lot in common with some of these deposits on Mars. And I realize, we've driven past this. We might go revisit Gusev, though, with Mars 2020. That's on the table as a landing site. But I think as we move forward in our Mars exploration, we need to be watching for these kinds of features so that we can target the best lithofacies and the best potential the potential lithofacies that have preserved the largest number of biosignatures, if they're there. Okay, so this is providing macroscopic recognition criteria for spring deposits. The other important takeaway is that this Ostwald ripening process is actually preserving these features on geologic timescales, and these springs. So therefore, these springs have a high preservation potential. So I'd like to thank my collaborators and some funding, and this is my son in the field. you.